In this video, we'll be discussing symmetry. A symmetric graph has the characteristic that their mirror image can be obtained about a reference, typically a line or a point. You have some experience with this when you have graph parabolas. We know that parabolas have an axis of symmetry, and then the mirror image is displayed on both sides of that axis of symmetry. It's the same idea, mirror image. We're going to be discussing three types of symmetry. Symmetry with respect to the x-axis, with respect to the y-axis, and with respect to the origin. I have about there in parentheses because sometimes you'll see it written symmetry about the x-axis or about the y-axis. Just two different verbiages that are used. So let's start by considering the point -2, 3. If I wanted to see where the point would lie if we had symmetry with respect to the x-axis, so here's our x-axis, that means that I would have the mirror image above and below the x-axis. Notice that that point is 3 units above the x-axis, so the mirror image would be 3 units below the x-axis, right here. This is the point -2, -3. Now take a look at the coordinates of this point compared to our original point. Notice that the y-coordinate has changed signs. So when we have x-axis symmetry, the y-coordinate changes sign. Okay, let's do the same thing this time with the y-axis. Here's our y-axis. If we want to find the point that would exist if we had symmetry with respect to the y-axis, that means it would have to match left and right side of the y-axis. Our original point, -2, 3, is 2 units to the left of the y-axis, so the symmetry point would be 2 units to the right of the y-axis. This is the point 2, 3. Again, I want to compare this point to our original point. Notice that this time the x-coordinate changed signs. So anytime that we have a symmetry with respect to the y-axis, the x-coordinate changes sign. The last type of symmetry is symmetry with respect to the origin. And I definitely think that symmetry with respect to a point is much more difficult to visualize than symmetry with respect to a line. So what I always think of when I have symmetry with respect to the origin is diagonal symmetry. So our original point, -2, 3, is in the second quadrant. Diagonal to that is the fourth quadrant. So I should have symmetry between these two quadrants diagonally. So if we follow that diagonal line, we would have the point right here at +2, -3. That's the point we get for symmetry with respect to the origin. Take a look at its coordinates compared to our original point. Notice that both the x and the y coordinate change signs. That happens every time we have symmetry with respect to the origin. I like to do this introduction of symmetry because it's going to help us understand the tests for symmetry that we're going to learn next. We're going to be testing equations for symmetry. So let's start with symmetry with respect to the x-axis. I have the x-axis highlighted there in blue. A graph has symmetry with respect to the x-axis when it looks the same above and below the x-axis, as my graph in red does. Well, we've already seen that if the point AB is on the graph, then the point A negative B is also on the graph, that the y-coordinate changes sign. So how we're going to test an equation for symmetry with respect to the x-axis is we are going to replace y with negative y. Then we're going to clean it up. If the equation remains unchanged, which means if we get the original equation back, then the graph of the equation is symmetric with respect to the x-axis. Let's take a look at a graph that displays symmetry with respect to the y-axis. I have the y-axis highlighted there in blue. Notice that the graph matches on the left and right side of the y-axis. We've already discovered that if the point AB is on the graph, then the point negative AB is also on the graph. That is, the x-coordinate change signs. So the test for determining whether the graph of an equation has symmetry with respect to the y-axis is we're going to replace x with negative x. Then we're going to clean it up. If the equation remains unchanged, that is, we get the original back, then the graph of the equation is symmetric with respect to the y-axis. Now, if we don't get the original back, then the answer is no. Last one is our symmetry with respect to the origin. Notice the diagonal symmetry happening here. We've already seen that if the point AB is on the graph, then the point negative A, negative B is also on the graph, that both coordinates change signs. The test to determine whether the graph of an equation displays symmetry with respect to the origin is that we're going to replace both with the opposite. We're going to replace y with negative y and x with negative x. We're going to clean it up. If the equation remains unchanged, that is, we get the original back, then the graph of the equation is symmetric with respect to the origin. So we're going to be doing 3 tests for each equation. I do want to note that if you have symmetry with respect to both the x and the y axis, this implies symmetry with respect to the origin. So as you're doing your 3 tests, if you get yes for both the x-axis and the y-axis, then you automatically know that there's going to be symmetry with respect to the origin without even doing the 3rd test. It does not work the other way around, though. Symmetry with respect to the origin does not imply symmetry with respect to the x-axis and the y-axis. I mean, just look at that graph right here, to the left. It has diagonal symmetry, but it does not have up and down symmetry or side to side symmetry. So let's test some equations. We're going to use algebraic tests to determine whether the equation's graph is symmetric with respect to the x-axis, y-axis, or the origin. I like to make a little table since we're going to do 3 different tests and I want to keep track of what I'm doing. So, test for x-axis, y-axis, origin. And we're always replacing the opposite variable with the negative. So for x-axis symmetry, we're going to replace y with negative y. Doing so, we get x equals 2 times negative y squared plus 3. Now we want to clean it up. I have negative y in parentheses squared. So what's negative y times negative y? Positive y squared. This cleans up to be x equals 2y squared plus 3. There's no other simplifying that we can do, so now it's time to compare it with the original. Is it exactly the same as the original? Yes, it is. That means the graph of this equation will display symmetry with respect to the x-axis. Now let's test for y-axis symmetry. Here we're replacing x with negative x. We get negative x equals 2y squared plus 3. Now we want to clean it up any way that we can. Well, that negative x isn't raised to an exponent. It's not inside an absolute value bar. There's not really anything we can do to try to simplify this. One thing that we can try is dividing every term by a negative 1. Going to give us positive x squared equals negative 2y squared minus 3. That was really our only move. So now let's compare. Is that our original? No, it's not. So the graph of this equation will not display symmetry with respect to the y-axis. Last one to check is the origin. When testing for symmetry with respect to the origin, we're going to replace both variables with the opposite. So that'll be negative x equals 2 times negative y squared plus 3. We want to clean it up any way that we can. We do have negative y raised to the second power, so we want to simplify that. Negative y times negative y gives us positive y squared. That's 2y squared plus 3. I compare it with the original. It's not the original. I think, well, is there anything else I can do? My only other move is to divide everything by a negative 1. But we saw in the last example that didn't work here. I check again to see if this is the same as my original equation. It's not. So the graph of this equation will not display symmetry with respect to the origin either. It will only display symmetry with respect to the x-axis. Let's try another one. 3x equals y minus x to the third. I'm going to start by making my chart. It's important when you're doing assignments to put headings so that I know what you're testing for. And also when you're doing your homework, it's really important to do that so you know what you're testing for. So to test for symmetry with respect to the x-axis, I'm going to replace y with negative y. There's not much cleanup to do here. That negative y isn't raised to a power inside an absolute value, so I can't simplify it in that way. Try dividing all my terms by negative 1. Doing that, we get negative 3x equals y plus x to the third. We compare this with the original. It's not the same as the original. So the graph of this equation will not display symmetry with respect to the x-axis. Testing symmetry with respect to the y-axis, we're going to replace x with negative x. Notice that x shows up more than once, so be sure to replace both of the x's with negative x. We definitely have some cleanup to do here. On the left, we have a positive times a negative. Gives us negative 3x equals y minus Now, if you have a negative x raised to the third, that's a negative times a negative times a negative, that's going to give us negative x to the third. And then we want to rewrite that right side. Instead of writing minus a negative, let's make that y plus x to the third. Comparing it with the original. No, it's not the original. I can try dividing each term by -1, see if that helps. We get 3x equals negative y minus x to the third. Is that our original equation? No. So the graph of this equation does not display symmetry with respect to the y-axis either. The last one to check is origin. Here we want to replace both x and y with the opposite. This will be 3 times negative x equals negative y minus negative x to the third. Cleaning this up, this will be negative 3x on the left minus y minus, we saw for our y-axis test that negative x to the third gave us negative x to the third. And we can rewrite the right-hand side to be negative y plus x to the third. We've cleaned it up. We're going to compare it with the original. It's not the original. The only other thing we can do is divide every term by -1. When we do that, we get positive 3x equals positive y minus x to the third. Now we compare it with the original. And why, yes, it is the original. Therefore, the graph of this equation will display symmetry with respect to the origin.